So we have mesh. Hold on, I don't know. There we go. We have mesh. Zoom in. So mesh is the sister to node, obviously. So how KVL, I'm sorry. So how let's say it like this. So how node voltage corresponds to KCL, mesh corresponds to KVL. So it's literally a special version of KVL. Are you following me?
Yep.
Now the thing about mesh is there's no ground. And because there's no ground, that makes the signs really annoying. I think mesh is actually harder than node voltage method. In the beginning, it looks like mesh is easier. But at the end, when you start to consider the negatives that kind of just have to be generated automatically, I think mesh is harder. Honestly, though, to each his own, they're in the same bracket. And once you master one of them, you can basically use it for everything. I prefer no voltage method because it's easier to find. You can solve for open circuit voltages with no voltage method. You can't solve for open circuit voltages with mesh current as easily. You can do it. It's just not as easy. It's not as intuitive as with no voltage method. And at the end of the day, when you start to get to more complicated circuits, all your circuits, you have an entire circuit, all your circuits will have leads coming off the back where you can connect extra stuff. And so you'll always need to know that voltage. And because of that, people tend to just use no voltage method because it's a quick shot. But whatever. That's enough of that. We're gonna I'm gonna draw us up a circuit. I'm gonna put our rules and we're just gonna solve it kind of organically. Does it make some sense?
Okay. Yeah.
So here's let's start with something like this. I'll put a current source here. I'll put a resistor here, a resistor here, and a resistor here. Yeah, let's just do the simple circuit. We'll say that this is 2, 3, 6, and 2. Yeah, let's go with that. And then we'll say let's solve for the voltage and the current passing through this resistor. Make some sense?
Mm-hmm.
All right, so we're gonna solve for those bad boys, and we're gonna use mesh current. So the thing about mesh current is you don't need a ground. So step 1 for mesh current is very similar to step 1. Just like how no voltage method has 3 steps, mesh current has 3 steps. Only thing is every time you focus on voltage and no voltage, you focus on current and mesh current and vice versa. And that's how it's gonna be basically from now on, which is really, really convenient. As long as you know one, if you know you just have to do the reverse rule basically to figure out the other one. So what do I mean by that? How we would find how we label the ground and the currents, we're gonna do the reverse. There is no ground, which is nice. So you don't have to worry about that. But be careful. Be careful of negatives now, because the ground kind of got rid of negatives. So because you don't have any, you have to be careful of negatives. But we will label the voltages.
Oh.
And you're going to label our mesh loops. That's what we call them, mesh loops. What is a mesh loop? A mesh loop is the smallest loop that you can put on the smallest loop. It's your circuit divided into the smallest loops possible. Okay.
Mm-hmm.
And so I'm going to draw them up. So when we're doing KVL, let's take a look. When we're doing KVL, we could do, I'll put it in blue. We could do this loop right here, this loop right here, and the big loop. Make some sense?
Yep.
Your meshes are always going to only be the smallest loops. So what that means is I got to erase the big loop, but I'll take the 2 smaller loops that I drew up. Those will be my 2 meshes. Does it make some sense?
Mm-hmm.
All right, now when it comes down to mesh, you can draw the loops in any direction you want. Just like how you can draw the currents in any direction you want on a no voltage, you can draw
You gotta stay consistent.
Huh?
But you gotta stay consistent.
You have to stay consistent mathematically. But however you draw them, as long as you draw them and do your math in correspondence to the way you drew them, you'll get the right answer. Of course, I have a way that I like to do it. I like to try to make sense out of it. I always say current leaves the source. And so I'm going to have my mesh go like that. And what I try to do is I don't always succeed, but I try to have the currents that pass through multiple all go together. And so what that means is instead of doing it like this, which is perfectly fine, you know what? I'll actually do it like that. I do it like that. I want you to see something. You do it like that. And this is what I mean by the negative. So I'll actually put it just like this so you can draw your negatives. So you're going to see some people just always do clockwise. You're going to see some people always do counterclockwise. And you're going to see some people do both in one problem. If I were to solve this problem just without teaching you, I would have actually done this. I would have done the opposite direction. But I want to show you the negatives that I was talking about. So I'm going to do it this way because I just introduced negatives. And sometimes you're not going to be able to dodge them, obviously. So you're going to draw your mesh and we're going to label our voltages. So I'll label, remember, voltage always goes plus to minus based on the current. So if this current goes like that, then I'm going to make the voltage correspond to that. So I'm going to go plus minus. Make some sense?
Mhm.
I already drew that voltage as plus minus. So that's stuck for you. And if this guy goes like that, then that means that his voltage goes plus minus. So I've just drawn my voltages. Cool?
Mhm.
Awesome. So I label all my voltages and I label all my mesh loops. Done. So that's step one. Very similar to no voltage method. Step two in no voltage method would be to look at your voltage sources, right? And then see how they get your answers. See if any of your voltage sources give you automatic voltage answers. So for mesh current, you're going to look at your current sources. Use current sources to build equations. Actually, you know what? I'll say it like this. Build equations for your current sources. I sources. So what does that look like? In node voltage method, in the method that we used up here, we did this step right here. We did each voltage source and said, okay, because of the way that the equation is, VA automatically equals 10. And because of the way that this is, the dependent source couldn't really equal anything, but it would have been nice for it to equal something. We're going to do the same thing for mesh current, but we're going to do it for the current source, okay?
Mhm.
And now this is the reason why I tell students, you got to master one like perfectly first. If you do not master one of them first, you're going to confuse them because they do the same thing backward. And if you don't have all your ducks in a row, you are gonna get your wires crossed. Like I promise you, if you do not master no voltage first, trying to go to mesh current and learn at the same time, you're gonna screw yourself. What does it look like though for this problem? We're gonna focus on, we're gonna draw an equation for this guy. So I'm gonna say, oh, I'm sorry, I didn't label my things. You gotta label them A and B. You're gonna give them labels just like you would give your nodes labels. I messed you up for a second there. So this guy will look like this. You see how IA is coming up and through it?
Uh-huh.
You see how there's no other current touching, no other mesh loop touching that current source?
Mhm.
That means that IA has to be 2 because that's the only current interacting with it. And so you would literally say IA equals 2. And I'm going to put a plus IA because the IA is going in the direction of the 2. It's going upward. Make some sense?
Yep.
Whereas if I were going downward like this, I would have
It'd
had
be
to say negative. And so that's what I mean by watch out for your negatives. You see that?
Mhm.
So that's why I like to have my currents go in the direction of the source. So that I always end up with a positive. Just like how when I'm doing my voltage sources, I like to put the ground on the bottom so that I get VA minus VG equals my number instead of VG minus VA equals my number. Because this right here will give you your negative, and that happens if you put a ground on the top. You see that?
Mhm.
And so it's just setting up little things so that you can kind of dodge negatives. Once you know what you're doing, negatives will be the answer, the reason why you get the answer wrong. So bam, I've done my step 2. Step 2 is done. I already figured it out. We're good to go. And with that, we already figured out this whole loop. That whole mesh has already been figured out. Just like how in node voltage, the whole goal was to figure out the voltage of each node. That's our goal on no voltage, right? In mesh current, our whole goal is to figure out, let me see if I get my eraser. Our whole goal is to figure out everything in both meshes, every mesh value. Make some sense? So we just figured out IA. Now we got to focus on IB. Well, obviously, IB isn't touching any current sources, so I can't use a current source to figure out IB. And so that's where you're going to go to step 3. So for node voltage method, your step 3 was to do KCL, the current law, on your extra nodes. So we're going to flip all of that around for mesh current. In mesh current, you're going to do KVL, the voltage loop rule, on all excess loops. Does that make some sense?
Yep.
Okay. And I'm saying it, but if you want me to write down like explicitly the rules for voltage method next to it so that you can see exactly how they parallel, I can do that for you. I'm just writing down the mesh current just because I'm being lazy and I feel like you're able to catch on with me.
No, yeah, I'm catching on what you're saying. I'm just gonna see what you do, how you do your KVL with the excess loop.
Dope. So now we're gonna do our loop B.
IB.
So loop B, what we're gonna do is I'm gonna start you off nice and slow. Look at the direction that B is going. B starts up here and then it ends at the bottom. So I'm gonna start right there. Does that make some sense? All right. So I like to do it like this. When you go from plus to minus, we're looking at voltages. When you go from plus to minus, you're dropping the voltage. You're falling. You go from high to low, you're falling. So it's going to be minus the voltage on 2 because I'm going from the plus to the minus. Make some sense? I know every professor does it a little bit differently. Some professors always do pluses. I like for it to make sense with respect to how I think it works. So I'm going down this voltage. There's nothing here. And then I'm going to go from my negative to my positive. You see that? So I went up in terms of voltage. From minus to plus is up. Hold on. I don't want to mess myself up. Yeah, I'll put a little, you know what? I'll put it in gray. Bloop, bloop, bloop. Start there. All right, dope. And then I'll go around like that. Perfect. So that was a minus V2. And then I have to go up the V6. And that has to equal 0. And that's my KVL equation. Make some sense? So obviously we can't have it like that because everything has to be written in terms of IA and IB. So I'm going to rewrite the voltage in terms of current. So we're going to use Ohm's law. We know V equals what for a resistor?
I over R.
I times R. V equals R. And so it's going to be easy enough to just plug and chug that boy back into this. And so what it looks like is this. V2 is going to be negative on the outside. And we're focused explicitly on this 2 right here. Make some sense? Which loop? Is it A or is it B that's touching the 2 ohm?
IA.
No, IB.
IB.
Oh, that's what's touching.
The current swing.
So that's going to be the current that touches it, IB, and then you multiply it by 2 because that's the resistor.
Okay.
And then you do the plus, and that's what's happening here. The minus goes to the minus, the plus goes to the plus. And I always do mine this way because I mess up mesh current. I'll say it like this. Out of all the techniques, mesh current is my least favorite one. That's the one that I mess up on the most because of this. I used to do it where I wouldn't write the V's. I used to not do this step. Now when I do mesh current, I do this step every time. Even though it's a baby step, I do it every time so that I assure my answer. Because I've messed it up so many times, recently even, that I was like, you know what, forget it. I'm always going to do this baby step, even though, you know, I shouldn't have to. The fact of the matter is I always mess up the negatives. So I'm just always going to put that baby voltage step so that I can see what I'm doing. So plus, and then what we're going to do is we're going to look at this 6. So here's my question. Which of these, A or B, which of those are touching the 6?
Both.
Both, exactly. Both currents are touching the 6. Both currents are touching the 6. So what happens
So is
is
it IA minus IB
that's exactly right. It is IA minus IB times by the 6,
6? Yeah.
and now that equals 0. But here's my question. Why did you say IA minus IB and not IA plus IB?
Because we're going with the current flow, and the current flow on IA was positive, and you see the current direction is reversed on IB.
Yes.
It's touching, so you know that it's negative.
You said it perfectly.
Out.
You said it perfectly. This current right here is going down. IA is going down, so that's going to be the positive. IB is going up, so that's going to be the negative. And that's why this is positive, and that's why you put the minus there. You said it 100% right.
No. Or you could say like, oh, going in and then leaving. If you want to talk about terms of like how you gave me the memorization.
Wait, say it again.
I was saying like how you help me memorize it. IA is going in, so it's going into that current source. So you see it's positive, and then IB is going out.
Yeah, no, that's good. I like that. However, you need to kind of perceive it to make it stick is what works for me.
Yeah,
but at the end of the day, we're going to do this a couple more times so that you can see that this is going to change up as you draw it, but the answer is going to be the same. So, bam, we put it just like that, and all we have to do now is solve because we know IA is 2. So I'm going to plug in my 2 for this guy, and then I just got to solve. So I got negative 2 IB, negative 6 IB is negative 8 IB. I'm known for just putting B, but negative 8 IB. Equals negative 12. 6 times 2 is 12. Positive. IB is going to be 12 over 8, which is 4 over 2. No, 3 over 2. 1.5. Bam. I figured out IB. Make some sense?
Mm-hmm.
Now, that's not the answer, though. What I've done is I just solved for IA and IB. IA was 2. IB is 1.5. Good. I just did exactly what I did for my no voltage. I figured out everything in terms of my 2 meshes. Okay. Also note that IB is positive, which means that this actually would be the right direction to draw it. That counterclockwise that we put. If it were negative, that just means that it will be in reverse. That's all it means. Makes sense?
Polarity.
So, with that being said, now we got to take a look at the actual current and voltage. So we're gonna go the current through the 6 equals, and so we got to take a look at it. The current through the 6, is that current B or A or both?
The difference between them?
Yes, exactly. The current through the 6 is going to be IA minus IB. Because the 6 is going down.
0.5 amps. Yeah.
Yes. 0.5 amps. And then the voltage on the 6 is just going to be, we know V equals I times R, right?
Mm-hmm.
And so it's going to be this guy. Because the I is always IA minus IB for the 6. It's never going to just be IA or IB because both of them are interacting with the 6. Now, in real life, are there 2 currents passing through the 6 at the same time? No. In real life, no, that's not happening. But this is something like a superposition where if you look at one effect and you look at the other effect, you can add them together to get the net effect. So in reality, the current really is going down through this guy. Like it is going down. It's just not going down as much as IA says it's going down. Does that make some sense?
Yeah.
That's all. So we got that. So we have to multiply it times the 6. So it's 0.5 times 6, which would be 3. And that is how you get your answer there.
Mm-hmm.